Okay, today we are going to review a new chapter which is about ensemble techniques. It is not related to classification. It's basically a new concept related to data mining, machine learning. So to start, so let's take an example. Let's say we want to purchase a new car, and so first what we will do, we will try to walk up. Are we going to walk up to a first car shop or purchased one based on the advice of the dealer? So it's I if we ask a question of using these two scenarios, so it's highly unlikely, and we would basically likely uh, browse a few web portals where people have posted their reviews and compared different car models. So checking for their features and prices of the car. Then we will also probably ask our friends, colleagues for their opinion. So, in short, to conclude, so if we wouldn't directly reach a conclusion, but will instead make a decision considering the opinions of other people as well. So, ensemble models in machine learning also operate on a similar idea. So, here they combine the decisions from multiple models to improve the overall performance. So, ensemble techniques, it presents the techniques for improving classification accuracy by aggregating the predictions of multiple classifiers. And these techniques are also known as ensemble or classifier combination methods. So, the ensemble methods actually constructs a set of best classifiers from training data and performs the classification by taking a vote on the prediction made by each base classifier. The ensemble methods are techniques that create multiple models and then combine them to produce the improved results. And the ensemble methods usually produces more accurate solution than a single model would. So basically in an ensemble method technique, we rely on various models before coming to an conclusion. Let's see how an ensemble methods work. So let's say there are multiple classifiers. So based on the multiple classifiers, we will make a prediction. So let's say if the base classifiers are identical, then all the classifiers, base classifiers will commit a same mistake. So thus the error rate of the ensemble may remain. In this case, basically 0 equals to 0.35. So on the other hand, if the base classifiers are independent, and their errors are uncorrelated, then the ensemble makes a wrong prediction only if more than half of the base classifiers, uh, that is your half will be approximately 13 out of 25. So half of the base classifiers, that is 13, will predict incorrectly. So for this case, the error rate of the ensemble classifier is given in this formula, which is calculated that you see here, using this error rate 0.35 as E, and here the value comes as 0.06. So it is considerably lower than the error rate of the base classifier, that is 0.35. So in the graph, actually here in the plot, it shows the diagonal line represents the case where the base classifiers are identical. Okay, and while the solid line, the curve line, represents the case in which the base classifiers are independent. So here the ensemble classifier performs worse than the base classifiers when um, the E value is greater than zero point 0.5 here at some point here. Then let's see what is the general approach of the ensemble technique. So this explains the methods for constructing an ensemble classifier. The basic idea is to construct the multiple classifiers from the original data and then aggregate their predictions when classifying the unknown examples. So there are different ways in which the ensemble classifiers can be constructed. Here, as you see in this picture, from the original training data, the multiple base models learners are created, which are the C1, C2 up to CT like this. Then for each models, a sample data set is provided to each of the model, and the data sets are here, D1, D2 up to DT. So in each step, when we provide the next sample of data set to a given model, the samples are randomly resampled and fed to the model CT. See, it can be C1, C2 up to CT. Um, just for notation, I'm just saying that it is CT. This process is called your row sampling with replacement. We will see that in an example also. So subsequently, then each model city will be trained on each sample dataset, that is DT. So now let's say we want to predict a new dataset, right? Then it will be provided to each model city, and subsequently every model will give outputs, and then for each output a voting method will be applied, and where the majority of votes will be given by classifiers. And so now all the outputs will be combined, and through majority voting the output is determined. So let's say we have let's say we have an output of one moment, we have an output of 1, let's say here 0, 1 and 1. So through the majority voting, as per the majority voting, the outputs will be combined, and the final output 1 will be considered as 1 has a majority voting here. So there is a concept called bootstrap. So bootstrap is a method through which training dataset D is sampled multiple times through multiple datasets, that is DT provided here and provided to the model in turns to the city. And there is another one concept called aggregation. So aggregation is the process which combine multiple models to get output through the voting classifier. This is the basic general approach for your understanding. Then types of ensemble methods. So the most popular ensemble methods are basically boosting, bagging, and stacking. And ensemble methods are ideal for regression and classification, where they reduce bias and variance to boost the accuracy of the models. So first, by manipulating the training set created by resampling the original data according to the to some sampling distribution and constructing the classifier from each training set. So two example of the ensemble methods that manipulate that training sets are basically the bagging and boosting. And then if we take in terms of manipulating the input features, then a subset of input features is chosen to form that training set, and the technique is actually the random forest. Let's see an example. So we will now basically look into the process of bagging. So bagging is a method of generating the ensemble of classifiers, a collection of classifiers, and here the base idea is to manipulate the training sample. And let's say there are n equals to number of samples present. So here first in the original data, you can see there are 10 data points. Then there we apply 3 steps of bagging or random resampling, where the data points are sampled through multiple iterations. Okay, and see, it is not easy to see how the bagging actually appears. It is actually will be easier to track through the code. the implementation. So each round of bagging are nothing but the random resampling method. So they are resampled through multiple iterations to have same number of data points in the end. That is the 10 data points you can see at the end of the third round of the bagging. So if we have n, that is number of samples, n number of samples, then each sample has a probability of 1 minus 1 by n to the power n of being selected. This many number of samples has probable this many number of samples will probably be selected at the end of the bagging round. And to see the algorithm, if you see the steps how the bagging is performed, the main steps are creating multiple data sets. So first we do the sampling with a replacement in the original data. Okay, in the original data we do the perform the sampling with replacement, and then new data sets are formed from the original data set. Then while building the multiple classifiers, so on each of the smaller data sets a classifier is built. Usually the same classifier is built on all the data sets. Then, while combining the classifiers, the predictions of all the individual classifiers are now combined to give a better classifier, usually with a very less variance compared to before. So, these are basically the steps how the bagging is performed, and it is given through this algorithm. Let's see an example. So the original data is given, and for each data point, the label is also given in the Y. The data points are given in the X row. So let's X denote the one dimensional attribute and Y denote the class label. So suppose we use only one level binary decision trees with a test condition X less than equals to K, where K is the split point chosen to minimize the entropy. If you remember the decision tree, how entropy is calculated, so that same entropy will be applied. So the split point, the I mean through the number of bagging steps, how the split point will be decided, it basically determined through the entropy. And this type of determination of split point through entropy is called the decision stump. So here each classifier is a decision stump. So without bagging, the best decision stump we can produce the splits, the instances at either 0.35 or your x less than equals to 0.35 or x less than equal to 0.75, and the y values are determined as if the x value will lie in between 0.35 and 0.75, then the y values are taken as -1, otherwise they are taken as +1. This is a criteria that we will obey for our one dimensional data set. And in each steps of bagging, this same formula or same criteria will be applied. So let's see the example. So here in this particular example, the K is considered as 0.35. Okay, and this determination, split point determination, is done by taking into account the entropy. So K is considered as 0.35. So if the X value is less than equal to 0.35, then Y value is determined as 1. Another one condition, if X is greater than 0.35, then Y value will be -1. Okay, but if the X value is less than greater than 0.75, the criteria that I was saying is telling you about in the last slide. So if x value greater than 0.75, then also the y value will be +1. So you can see anything below less than or equals to 0.35 is +1. Anything above 0.75 is also +1. Anything lying within that range that I was just saying, they all the labels are being classified as -1. We always will obey this criteria. So let's see the another rounds of the bagging. So in each step, the right hand side, the value shows actually the decision stump being chosen for each round. So based on this decision stump value x on the right hand side, the y value are chosen by the formula. So if we have a like x value falling within the range of 0.35 or 0.75, then the y values are taking -1. Otherwise, they are taken as +1. So every step considers randomly the decision stump as shown on the right hand side. Then in each step, the right hand side, the same thing that I just told you in this step, the same thing also goes on the all the rest of the bagging round. And here we have all total 10 rounds of bagging. So after all the rounds of bagging, we need to find out a summary of the training sets, where we need to keep a track of all the bagging rounds, what are the split points and what are the left class, right class labels. After we have them, next step is to finally predict the class uh, as shown in this table. So each point is labeled to categorize with a ground truth result as the highlight row that you see here with the red line highlighted row. And for each round, the labels are added together. The sum row actually gives the output. So based on the sum row output, the sign or the label is decided. Okay. So in each round, whatever labels you have, just write it down for all the bagging rounds. Then you just add them together. So whenever there is a positive sign, sum result, you just take the label as +1. Otherwise, the label will be -1. So in this way, you will predict. So this is all about bagging. Then next, let's see the another one methodology, that is boosting. So boosting refers to a family of algorithm. Here we basically have same rounds of resampling, but here it is a little bit different to the bagging methodology. We will see how the boosting actually is carried out. So boosting basically refers to family of algorithms which converts weak learner to strong learners, and it is an ensemble method for improving the model predictions of any given learning algorithm. And the idea of boosting is to train weak learners sequentially, each trying to correct the predecessor. Here, let's see an example. Um, boosting is actually done by building a model by using the weak models in a series. So, in the first step, a model is built from the training set data, and then a second model is built which tries to correct the errors present in the first model. This process is continued and models are added until either the complete training data set is predicted correctly or the maximum number of models are added. So here we have 10 set of data points in the original data set. Then three rounds of boosting will be applied. In the last round, the sample 4 is actually misclassified and most likely their weights will be increased as they are misclassified. This is the main difference in between the bagging and the boosting. So if something is misclassified here, as shown the example of force, so their weights will be increased, and the correctly classified samples that 8, 10, 5, 6, 3, their weights will be decreased. So in the next label of boosting, the emphasis of classification will be on the samples whose weights are increased, and here in this case are 4. Okay. So then next, looking into the actually the ADA boost is basically a really successful boosting algorithm which is developed for the purpose of the binary classification. It is also called adaptive boosting. Okay. So ADA boost has various steps. Actually, the steps basically rely on the initial base classifiers created from the original data set. Then we still have um, the split criteria, right? So the split criteria, so those criteria, and through different rounds for determination of the labels, we need to rely on the error rate and the importance of the classifier or the performance of the classifier, and their formulas are given in this way. So, and as I was showing you, for the misclassification, we need to do the weight update, whether weight will be increased or decreased. That thing is given by this formula here. Then, while doing the classification, if in between the rounds they produce an error rate higher than 50%, so if the error rate is higher than 50%, then the weights are reverted back to 1 by n. So n here is your number of classifiers, how many number of classifiers are actually there, and the resampling procedure will be repeated. This is the basic algorithm for the ADA boost. Let me show you one example through which it will be easier to understand what is going on in here. So here see there are 4 pictures. Okay, the diagram here explains the adder boost algorithm basically in a simple way. So let's try to understand it in a stepwise process. Here see the B1. B1 here consists of 10 data points. So here plus minus signs, if you count them, it will be 10. 10 data points which consist of 2 types of data points. So namely the plus sign or the minus sign, and 5 of which are plus and the others are minuses. And each one has been assigned equal weight initially. The first model here actually tries to classify the data points, and it generates a vertical separator line, but it wrongly classifies 3 plus as minus here in this red group. So here it is, this section is showing the wrongly classified points. Then B2 consists of 10 data points from the previous model, in which 3 wrongly classified plus are weighted more, so that the current model tries more to classify these plus signs correctly. And this model generates a vertical separator line which correctly classifies the previously wrongly classified plus. But in this attempt, it wrongly classifies 2 minus signs now. So now B3, what it will do, will consist of 10 data points from the previous model, in which 3 wrongly classified minus are, weighted more, so that the current model tries more to classify these minuses. The emphasis will be on the um, more weighted data points now, whose weights has been increased. And this model generates a horizontal separator line which correctly classifies the previously wrongly classified minuses. Now B4 will combine together the B1, B2, B3 in order to build a strong prediction model which is much better than the individual model used. And this is how the correct classification is performed. This is the basic ADA boost concept. Now, looking into an example, we are basically taking the same type of example. Mm, Here, same x 10 data points are there, and y it provides the labels. And the decision rule, we still use the same decision rule. If the data point lie in between 0.35, 0.75, then y values are taken as -1, otherwise they will be +1. Then performing the boosting rounds on the data set. The three labels of boosting rounds are shown with the split points and the class labels, and the split points are again determined by the entropy calculation. Okay, so whenever through the, let's say there are three boosting rounds, right? So in each step you need to determine the split point. What are the split point we got through the entropy calculation? Then write down the left class, right classes. So based on the misclassification, you need to perform, you need to update the weights, and those updated weights are provided by this column alpha. Now here in each boosting round, the weight updates are provided and the final classification is shown in this table, and the predicted class is shown by the application of the majority voting scheme. So in each round, data points are there, and each round, based on the classification, how the weights are getting updated, that is shown. Then using all those, you look at the labels of determination, how the labels has been predicted. Then after that, you can add them together to get the sum, and from there you determine the label based on the positive or the negative sign. And then based on a majority scheme, you determine whether it will be a plus or a minus, that is a negative sign. So this is all about this ensemble techniques. We are basically done with this chapter now. So as I have discussed already that next week, okay, next week Tuesday, we don't have a formal class. Okay, basically the time will be given to you for the preparation. Take the time of 5 days for the preparation to attempt the test on the 6th. Okay, if you remember, we have a final test on the 6th, so be prepared, and all the best to you. So there will be no formal class on the 4th, but if you have any questions, you can let me know. We can schedule a meeting to go over your questions.
Will you be posting?
Yes, go on.